Good afternoon. I'd like to welcome everybody to this doctoral thesis defense. And of course, a particular welcome to the doctoral candidate, Mirko Salewski, and the two official opponents, Professor Richard Dendy, Center for Fusion, Space and Astrophysics at the University of Warwick, and Professor Ambrogio Fasoli from the Swiss Plasma Center at the École Polytechnique Fédérale de Lausanne. Also, a welcome to Professor Henning Friis Poulsen from the Department of Physics at the Technical University of Denmark, who's the chairman of the committee. My name is Rasmus Larsen. I'm the provost and an executive vice president at this university, and I'll be the chairman of the proceedings this afternoon. The doctoral thesis, which is entitled Fast Ion Diagnostics in Fusion Plasmas by Velocity-Space Tomography, was handed in on March 14th last year, and the assessment committee was appointed in June 2019. And following the assessment committee's positive assessment, the doctoral thesis was accepted for defense by the Academic Council on November 29th last year. So the afternoon's proceedings will be as follows. So after my small introduction here, the doctoral candidate will present his thesis in a lecture of approximately 30 minutes. Thereafter, we'll have a small break, and then the first opponent will come to the podium and enter into a scientific discussion with the candidate, and thereafter we repeat with the second opponent. The chairman of the committee has already announced that he also has a series of questions that he would like to ask to the candidate. And if there are anyone from the auditorium that would also like to ask questions, please register with me in the small break after the lecture. I should inform everybody that the defense proceedings are being recorded, both sound and images, for documentation and also for the benefit of all of those who could not be here today. Now, after the lecture and the discussions with the opponents, the formal part of the defense is over. The assessment committee will withdraw to make their conclusions on the decision whether or not to recommend to the academic council that the degree should be given to Mirko Salewski. When the committee returns from their discussions, DTU will host a small reception in the lobby just outside the auditorium, and would like to invite everybody to join that small reception at that time. Now, on the occasion of a doctoral defense in physics at DTU in 2020, it's impossible for me not to mention that in 2020 we will be celebrating the 200-year anniversary of the discovery of electromagnetism by Hans Christian Ørsted. So we at DTU will lead a national dissemination initiative with many partners celebrating the curiosity-driven scientist and the impact of science through engineering and industrial ingenuity on our society. It is the plan that more than a third of our population in Denmark should participate in at least one of the events that we are organizing this year. Hans Christian Ørsted visited École Polytechnique, the other École Polytechnique, in Paris and brought the idea of a polytechnic school to Denmark. He took the initiative to form this university and was its first president from the start, from the beginning in 1829 until his death in 1851. Hans Christian Ørsted himself defended his doctoral thesis in September 1799. And with this, I would like to invite Mirko Salewski to the podium to present his work and his doctoral thesis. So please, Mirko, come up here.
Thank you, Rasmus. That's some pretty big footsteps you got there. Okay, good afternoon and welcome to my Dr. Technicis defense. Rasmus told you the title of this defense, and he also told you that I now have approximately 30 minutes to present an overview of this thesis, which is really the sum of 10 years of research that I did here at DTU. This overview has 3 parts. In the first part, I will tell you what this thesis is all about, and the short answer is it is about measurements of velocity distribution functions in magnetized fusion plasmas. In the second part, I will describe why we need to do this research, and in the third part, I will describe how such measurements are made. And here the short answer is that we formulate a tomography problem in velocity space and solve that. Velocity distribution functions, the concept is not new. It dates back to Maxwell in 1859, and he singled out one particular velocity distribution function based on 2 requirements. First, it should be isotropic, which means that any direction is the same. And second, the coordinates should be mathematically separable. And the Maxwellian is really the only distribution function that fulfills both requirements. Then 8 years later, he dropped the second requirement and instead showed that collisions do not actually change the Maxwellian. Then Boltzmann showed 10 years later that collisions will in fact drive any arbitrary velocity distribution function towards the Maxwellian. So these developments and insights were really important for physics, and they are the birth of what we now call statistical physics. The Maxwellian is really an excellent approximation for really many gases and plasmas in many, many situations. And so the Maxwellian and velocity distribution functions in general are taught in physics educations throughout the world and are described in many textbooks on physics, and even those on basic university physics that you hand to first-year students. In those books, the Maxwellian appears in either of these 3 forms here. You can have a distribution of the velocity component that looks like a Gaussian. It can take negative and positive values. The center of that is the average velocity, and the width is related to the temperature. And because of the isotropy, any other direction would look just the same. You can also have a distribution of speeds that looks like that. It's not symmetric. It can only take positive value, and it dips to 0 here, then has a maximum and tails off to infinity. And very similar is the energy distribution, now as a function of energy, which also goes to 0 here. And here I've chosen the parameters that are typical for ITER, 20 keV and 10 to the 20 particles per cubic meter. Given the isotropy, these 3 forms are really the same, and they are equivalent. They all mean the same thing. They show you the relative densities of particles with those velocities or energies. Fusion plasmas are not isotropic, so you can't describe them by just one coordinate as on the previous slide. But you don't need 3 coordinates either, and that is because particles gyrate really quickly about this magnetic field vector that we have in a magnetized fusion plasma. And because of that very quick gyration around this vector, the velocity distribution function becomes axisymmetric. And so we can get away with just 2 coordinates. And 2 common coordinate systems are shown here. I'm starting with that one. This is the parallel velocity and the perpendicular velocity, and I'm plotting here the Maxwellian from the previous slide. The parallel velocity is just the velocity component along the magnetic field vector, so it can take positive and negative values, just like the velocity component from the previous slide. The perpendicular velocity is defined like that, so it's more speed-like. It can only be positive, and the Maxwellian dips to 0 here. The energy distribution, that is usually, it takes a pitch as a second coordinate that runs from -1 to 1, because it's defined like that. So the pitch really shows you how compressed or stretched this spiral is. For pitches of -1 and 1, you have streaming along the magnetic field lines, and for pitches close to 0, the spiral becomes very compressed. You have a lot of gyration and not much streaming. Velocity distribution functions in fusion plasmas are also enormously important. They are basically described in any textbook on basic plasma physics. But until now, until this thesis, they could actually not be measured. And now I'll show you 3 examples of measurements of velocity distribution functions that we did within this thesis. This example here is from JET. And here we've got the parallel velocity and the perpendicular velocity. And those blue lines here are lines of constant energy. And I'm interested in the distribution function of particles faster than 120 keV. So the really energetic particles. And the first thing that you see that is this distribution function is absolutely not Maxwellian. It's not even isotropic. You've got a very strong tail drawn in the perpendicular direction, and there's not much going on here in these parallel directions here. That kind of distribution function forms when you shoot electromagnetic waves into the plasma, and the frequency of those waves is tuned to the gyration frequency of the ions. Then the wave energy pumps the perpendicular velocity of the ions, and you get this tail drawn in the perpendicular direction. Here in this scenario, we used actually the third harmonic of this ion cyclotron resonance frequency. And their theory tells us that there should be a region around 2 MeV and a little above where the coupling between the electromagnetic waves and the particle gyration becomes really weak. And therefore, we do not expect really a lot of particles to get accelerated to larger energies. And this is shown also in this simulation here. And our measurement could here confirm this the existence of this barrier region, and there's a good match between theory and simulation. The next example is from Aztec's upgrade. And here I'm interested in the velocity distribution function from 10 keV upwards. And this is now the pitch. And also this distribution function is absolutely not Maxwellian or isotropic even. That kind of distribution forms when you shoot neutral beam a beam of neutral particles into the plasma. Here you accelerate the particles up to 60 keV, and then they enter the plasma because they are neutral particles, and then they ionize here, and there's a small angle to the magnetic field that gives you a pitch of 0.6. So when they ionize, they form a source in the ion velocity distribution function right here, and from there they spread throughout velocity space by slowing down and pitch angle scattering. So there's several anisotropic features in this quite complex functions. There's way more particles for positive pitches as compared to negative pitches. You have the formation of those peaks. And here, just ahead of the peak, you have inverted gradients. And that means that the distribution function here is larger than at the lower energy here. That forms a source of free energy that can drive a lot of instabilities. Also, we have a numerical simulation here that matches very well with the measurements in the basic shape of this function. The last example is a measurement of the temperature and also of the anisotropic temperatures. Usually that is done by a measurement in tokamaks, by a measurement of the impurities that are in the plasma. In Aztec's upgrade we use boron. And that can be measured, the temperature of boron can be measured by measuring the Doppler broadening of line emission. So here in that case, we got a temperature of 7 keV up there. Then when you are interested in the temperature of deuterium, which is really the main plasma constituent, then you have to do a numerical simulation and calculate the transport and the implied temperature of deuterium. And that is found here to be 6 keV by that method. So if you have a measurement of the total velocity distribution function that we did here, so now we have to go all the way down to 0 in the energies, then we can calculate the moments of this velocity distribution function and get the temperature. The zeroth moment is a density, first moment is a drift velocity, and the second moment gives you the temperature. So here's the second moment that gives the temperature. And if you do that, then you find that the temperature is actually 10 keV. It's a lot larger than this computer temperature here, because here we account for the beam particles that have very, very high energies, and they enter the second moment here with a square, the velocities. So of course we get a very high temperature here. And I think these 6 keV, which is the temperature of a hypothetical Maxwellian that you think is not really experimentally testable. So I would not advise to use that temperature and instead use a total temperature. But this 10 keV doesn't really do the distribution function justice, because it is highly anisotropic, as you can see. An isotropic function would just have stripes. It would not depend on pitch. So instead, what we do is we calculate the temperature, the second moment, with a parallel velocity and with a perpendicular velocities. And then you find a parallel temperature of 9 and a perpendicular temperature of 11 keV, which shows then the anisotropy of that plasma. If you account for the beam particles together with these 6 keV, then you get similar values for those temperatures. Okay, now I want to describe why we need to do this research, starting from a helicopter perspective. So we have an energy problem, and that is the problem of two contradicting needs. We need more and more energy over time, and at the same time we need to reduce carbon dioxide emissions. So here we have got the annual worldwide primary energy supply from 1973 to 2017, and since then it has more than doubled. And down here you have got the distribution about of the various energy sources, and 80% of these three parts here are from fossil fuels, more than 80%. That hasn't changed a lot since 1973. If you use that many fossil fuels in your mix, then you get an increasing concentration of carbon dioxide. So shown in that graph here, the green curve from 1850, which is the Industrial Revolution, to now. And the carbon dioxide concentration has grown all the time. There's also two other greenhouse gases shown there. Because of the greenhouse effect, then that led to a larger temperature, and from 1900 to now, there's been a rise of about 1 degree in the temperature. Because of this temperature rise, the water expands thermally and the ice caps melt, and so you have a rise of the sea level here since 1900 of about 20 centimeters, and currently at a rate of about 3 to 4 millimeters a year. The greenhouse effect also leads to more frequent and more severe weather events and the extinction of many species. So about 60% of all greenhouse gas emissions come from the combustion of fossil fuels, and 40% come from elsewhere, like the agriculture or the building sector. But I think the conclusion is really clear. We have to switch to emission-free energy sources right away, as fast as we can. And there are various ways to do that: solar energy, wind energy, and hydro energy. And on the horizon, we will have fusion energy. And a fusion power plant would be fantastic, because it would deliver baseload power whenever you want it. And it would work like this. We've got a very hot plasma in a vessel, and the excess energy that is generated in this plasma ends up in a steam cycle and generates electricity. In that plasma, we have deuterium and tritium as fuels, and they fuse, and they react to helium, which is an energetic particle, and a neutron. And this energetic particle here then has a job to heat up the two fuels to this enormous temperature of 200 million degrees Celsius. So this really shows you that the energetic particles here are really at the heart of the fusion process, and they have to do the job right to heat up the fuels. So this is why we have to know where these particles are and what they're doing, and what their distribution function is. We found experimentally that energetic particles can sometimes have an enhanced fast ion transport from the core to the periphery. And this is because fast ions can be transported by instabilities in the plasma. And I'll show an example of that in the next slide. Fast ions can also drive instabilities themselves, and that's because their pressure is quite large, which led to the large temperature increase that I showed you. The distribution function is very non-Maxwellian, which I also showed you in 2 examples. There can be strong anisotropies, and there can be even peaks and inverted gradients. And because of their large speed, they can resonate with several waves that slow particles, which have temperatures of these 200 million, cannot resonate with. So this is my example of transport of energetic particles by an instability. Here we have a movie of the distribution function. This is the energy, and this is the pitch. And this instability that occurs here is called a Sawtooth Instability, and it's called that because time traces of various parameters like the density, temperature, and pressure have a sawtoothing time trace, like shown up here. This actually shows the fast ion density, which is obtained as a zeroth moment of that. So it's this integral here. And that shows that the fast ion density also has a sawtoothing time trace. So when this sawtooth instability comes to this strong dip here, then the particles are ejected from the measurement volume very quickly elsewhere. And that measurement volume here was in the plasma center. So they are they have gone to the periphery. And yeah, you can see that in the entire distribution function. In the next graph, I will calculate densities that are in different pitch regions. So this is shown here. The black line is the sawtooth crash that we had on the previous slide. This is now compared with the numerical simulation, which is dashed by the so-called Kadomtsev model. That model has a larger sawtooth crash than is supported by the data. But more interesting is how this sawtooth crash is selective in pitch. So if you compare the blue and the red curve, which is for large pitches, then both the simulation and the measurement have sawtooth crashes. But for the green line here, where the dashed line here, that's a model, has a sawtooth crash for small pitches, close to 0. But the experimental data just flat lines. So there's absolutely no evidence for sawteeth of these class of particles with very low pitches. Okay, then I come to the third part and want to describe technically how to actually do these measurements. And I call this method velocity space tomography. And in a nutshell, that works like this. We have 2 players. We have a distribution function f that we want to know about. And we have the measurements S that we have experimental access to by measurements with the fast ion diagnostics that are installed on tokamaks. Usually there is then a kind of forward model, usually a Monte Carlo simulation code. Given the measurement, given the distribution function, you can calculate an expectation for the measurement. That expectation can then be compared to the measurement that you actually make. And from the differences, you can hope to draw conclusions on the distribution function. That is done how fast ion diagnostic is done traditionally. I want to go the other way. Given the measurements, what is the most likely velocity distribution function? And because I have a model going from here to there, but not from there to here, this is an inverse problem. And because this distribution function is a 2-dimensional function, I can formulate this as a tomography problem and use all the methods that have been made in the tomography community. It is advantageous to rewrite, for tomography purposes, the forward model in terms of a matrix equation, where you then calculate a matrix that maps the distribution function on the measurements. And here are some example lines of that matrix. I've done this for 5 tokamaks, and I want to show just one example to illustrate how this really works in practice. Okay, at jet, this is a cutaway of jet, and this is a top view. And we have 2 lines of sight. One is perpendicular, that's up there, and one is oblique. And on top of the perpendicular line of sight, we have the time of flight spectrometer for neutron measurements, TO4. And on top of that, you have a high purity germanium detector that gets energy spectra of gamma rays. here on the oblique view, we have two neutron emission spectrometers, and one is based on a diamond detector, and the other one is a liquid scintillator detector. So those are the four diagnostics that we have available. Then let's look at the data that those diagnostics produce. I'm starting with the neutron measurements. Up here you have a time of flight spectrum. So this is a flight time and this is a number of counts that is produced by the time of flight spectrometer TOFOR of neutrons. And this flight time is really the time that the neutrons need to go through the entire detector. That's about 1 meter large, and they need about 20 to 100 nanoseconds to make it all the way through that detector. And then TOFOR counts how many times each event occurs. This detector here is a diamond detector, and that measures instead how much energy a neutron that bashes into the single crystal diamond lattice deposits there, and then it counts each event. That can be calorically measured. And then the last measurement is this, which is a liquid scintillator detector. So here the neutron bashes into a scintillation material that generates a light flash that is related to the neutron energy. And then it is counted how many times each light flash was observed. And here the units are a little peculiar. They give it in terms of mega electron volts of an equivalent electron that would have caused the same light flash. So these three measurements here are all neutron emission spectrometry, but the units are very different, and I think you will agree that it is very hard to comprehend them and interpret them in terms of what they really mean for the velocity distribution function of the ions in the plasma, even though those are supposed to be the measurements for this. Okay, the yellow data here is what I'm going to use for the inversion, and I can write all that in the right-hand side of this matrix equation. Gamma ray measurements with a high purity germanium detector look like this. So here you've got the gamma ray energy, and then each of these peaks is caused by a reaction that generates gamma ray. And those new detectors based on high purity germanium are so high resolution that they can even measure the Doppler broadening of these peaks. And this is how the data then looks like. This data is also written on the right-hand side of the matrix equation. Now we need to worry about the left-hand side. And here the starting point is the definition of a weight function by Heitbrink, 2007 PPCF. The weight function is defined like that if you multiply a weight function and multiply it by the distribution function and integrate it over velocity space, then you get the signal on your detector. So that really means that the weight function shows you how much signal you have per ion resolved in velocity space. If you then discretize that equation and write it for each data point of your measurements, then you already have this matrix equation here that we'll need for tomography. Okay, here's an example how the weight functions actually look like for the time of flight spectrometer. So I'm starting with that measurement. So this is neutrons that pass through the detector in 40 nanoseconds. This is the corresponding weight function. So this tells you that in this white region here, no signal is generated because these ions here have so low energy that they cannot possibly generate a neutron that makes it through TOFOR in 40 nanoseconds. And only those up here have enough energy to do that. Then for 50 nanoseconds, the weight function moves further down. And for 60 nanoseconds, it moves yet further down. So now almost all velocity space can generate neutrons at 60 nanoseconds. Now that can also bring me to how I determine the yellow regions here of the data that I use for the inversion. So if the flight time becomes slower and slower, then the weight function moves further and further down. And at some point, it becomes sensitive to these ions here of 120 keV, which I'm not interested in because they are neutral beam generated. So I discard all that data here. And if you go to the high-speed side, here to 25 nanoseconds or so, the weight function moves further and further up. And at some point, it leaves the picture entirely, and then it doesn't contribute to the inversion problem anymore. This exercise can then be repeated for the 5 detectors, and it looks like this. This is the 5 detectors. And this is for low, medium, and high signal shift. And the pattern is all the time the same for all these 5 detectors. I want to make one other point, that is that weight functions that sit on the perpendicular line of sight are symmetric, which is this one, and the top one. But the ones from the oblique view are lopsided, which is like that one. And that fact is going to haunt us when we study velocity space sensitivity for eta towards the end of this talk. Okay, all this data can then be written on the left-hand side of the equation. So now the problem is clear. We have the left-hand side W and the right-hand side S. All we need to do is now solve that for F. And you might try a least square fit as a first trial, but it turns out that that doesn't work because the problem is ill-posed. And that means that if you perturb the data by a little bit, then you get a large perturbation in F. So your image is just going to be dominated by random jitter. This problem was also encountered and solved by Tikhonov, and he modified this least square problem here by a second row. So the upper row is just the original least square problem, and the lower row penalizes some undesired property of F. And for example, if you use L as a first order gradient operator, then you will penalize strong gradients in the solution. So that will select for smooth solutions and get rid of spikes. And this parameter lambda here then balances the two requirements that you have on the one hand to fit the data, but on the other hand you also have a smoothness requirement. Then you also have prior information, and we know for sure that this distribution function is not negative. So we then can solve this minimization problem, and the solution is this distribution function that I showed you on the very first example. So just to summarize that, we have these 5 different spectra, and the units are quite incomprehensible for humans, and they are, of course, doable for experts. Each data point in each of these spectra has its own velocity space sensitivity. And so all that data can then be summarized and condensed into just a single picture of the velocity distribution function that can basically be interpreted by plasma physics students after about the 4th lecture in our own course. Okay, the last point I want to make is a look into the future. And in the fusion community, we are waiting for the eta tokamak that is soon going to be ready. And at the eta tokamak, we'll for the first time have a very substantial alpha population, 100 megawatts of alpha heating that'll form like 2/3 of the total heating. So the profiles and the heating will be self-sustained. So we really have to know where the alpha particles are and what they're doing and what their distribution function looks like. So for that we have 3 detectors, or 3 sets of detectors. We have vertical gamma rays, the horizontal gamma rays, and a collective Thomson scattering system that we develop here at DTU. And unfortunately, all these detectors are perpendicular views with respect to the magnetic field. So that means that all their weight functions are symmetric. Okay, before I go ahead and solve the inverse problem with tomography, we should study the velocity space sensitivity of the entire set of diagnostics. And that can be done by adding all the weight functions together, and then we have an idea where in velocity space our set of diagnostic is sensitive. That is done in this figure here that has a footprint of each of these different diagnostics. And what we see here is the darker the color now, the better the velocity space sensitivity is, that from 1.7 MeV upwards, so in that area here, we have a really good velocity space sensitivity. And that is because there is a nuclear reaction of the gamma rays that has a resonance here. So this region here produces a lot of gamma rays, but that region down here, lower than 1.7 MeV, absolutely no gamma rays. So CTS, or collective Thomson scattering, is really the only diagnostic that can tell us anything about the alpha particles at all at ITER. So in that region, I think we'll have to retire to one-dimensional inversion techniques. This yellow region here cannot be observed at all at ITER. So now I'm trying a two-dimensional inversion based on the gamma rays and collective Thomson scattering. And this is done here. So I have some test function in the left column. Then I generate some synthetic measurements, add noise, and invert them back. And then I can compare my inversion with the original function and can see how I'm doing. That works really well for the upper two, where you have a classical alpha slowing down distribution, which is isotropic. It also works down for that type of function, where you have an up-down symmetry. Where it could be that alpha particles with large -1 and pitches of 1 are ejected symmetrically. That works well. But if you have an asymmetry in this, where, for example, here, only the alpha particles with pitches of 1 have been ejected, then the solution that I get from the inversion is still symmetric. And we understand why that happens. That's because all weight functions are symmetric, and that's because all views are perpendicular to the line to the magnetic field. So we cannot really tell if that's a magnetic field and that's our viewing line, if a particle traverses that way or that way. We can still tell how tightly the spiral is wound, so we have sensitivity to the pitch, but we don't know the sign of the pitch. That could be helped if we installed an additional gamma ray detector with an oblique view on ITER. If you have a gamma ray and then a particle comes that way, it's going to blue shift the gamma ray, and if it goes that way, it's going to red shift it. So then you have the information to track how that in which region this particle is. So that would be what we need to do. And I'm trying my best to have that detector installed at ITER. Okay, summary. This thesis shows velocity space tomography from the concept to the experimental demonstration that measures the fundamental velocity distribution function and its moments. It converts really complex measurement data to images that are straightforward to interpret. It reveals new physics, combines complementary diagnostics, optimizes fast ion diagnostic data sets, and it accounts for nuisance parameters. And in the future, we will need a toolbox of 1D, 2D, and 3D inversion tools for ITER. And we need automatically generated velocity space movies for immediate diagnostic after the discharges. And that movie that I showed took me, unfortunately, some weeks to compute. Then all that is left to do now is to thank my many collaborators. Many of them are in the room today. And the teams that are with the tokamaks and the funding agency, and in particular my 2 PhD students that have worked for a really long time on this problem. And without the help of all these people, I would have not found these beautiful structures in velocity space from the initial blur that we had 10 years ago. Okay, that's all. Thank you for your attention.
So thank you, Mirko. And then as announced, we'll have a small break here. And any unofficial opponents, please register with me in the break. We'll reconvene in the auditorium at a quarter to 3. So in 5 or 6 minutes. Professor Richard Dendy has arrived on the podium. And I now invite you to a scientific discussion with the doctoral candidate. So please go ahead.
Thank you. So thank you all for coming, and it's a tremendous pleasure to be able to participate in this next step in the 200-year saga, would be the word, of research into electricity and magnetism in this part of the world. It's also been a great pleasure to read Mirko's excellent thesis, and my line of questioning will be an attempt to explore why what you have done matters and how it fits into what is already known about plasma physics and about physics more generally, it's the nature of this operation that Professor Fazzoli and I will have to operate in the mode of advocatus diaboli. I understand you have a strong command of Latin, so my first question is advocatus second declension or fourth?
Wow. Okay. I don't remember.
Okay.
But I do have the great Latinum.
Thank you. Right. Okay, that's good. I mention this partly because at many operations of this kind at other universities, a certain amount of Latin does emerge, and it's great that we've managed to tick this box also here at DTU. Anyway, if you were not doing this work at all, a cynic would say every deuteron-triton interaction generates a neutron as well as an alpha particle. We can measure the neutrons. If we're just focused on plasma performance, why do we need to know any more?
Well, we need to have the alpha particles in the plasma core because they have the job to heat up the rest of the plasma to very high temperatures so you can have fusion reactions.
Okay.
So we need to know what the alpha particles are doing on their way. They could interact with instabilities in the plasma and get transported somewhere else.
Yes.
And then they do not do the job of heating the plasma.
Sure. That would, of course, still have consequences for the neutrons, less reactions, because the alphas are poorly confined, fewer neutrons. Again, for a cynic who's trying to decide funding, what is the added value that your alpha particle studies bring?
If the alpha particles are not in the plasma core, it's not only the neutrons, but it's also the distribution of the alpha particles that matters. So if the alpha particles are fast, then the cross-sections say that there's a lot of neutron generation. And if the alpha particles get slowed and transported elsewhere, then there's fewer neutrons to generate. And if you want to understand the mechanism why that happens, then you have to know what is happening in the plasma, not only the neutrons that have left the plasma already and don't really interact with the plasma instead of their birth, except for their birth.
Okay. And starting at the other end of the argument, a cynic with a different background might say, can we not do this from back-of-envelope equations? We know the source term, we know the physics of slowing down.
Yeah, I mean, there are several, the back of the envelope that would give you an isotropic alpha particle distribution function that's got a tail of the form 1 over velocity cubed plus the critical velocity cubed, and there's no pitch dependence. Yeah. But really in the plasma, you have a way more complex function. There's anisotropies due to various effects. And one effect is, for example, this the tilt of the beam angle, neutral beam, where one of the fuels has a differential velocity, so it has a parallel velocity with respect to the magnetic field. And because of that, the alpha particle distribution will also have already an anisotropic birth profile. Yeah. Then on top of that, you have the effects of the orbits. So the further you go out, then at one point you measure more the inner leg of the so-called banana particles, and even further out than the outer leg. So then there is the second source of anisotropy. And then lastly, if there are modes like alvinic modes, that will also be anisotropic in velocity space. So these first two effects already have an anisotropy of about 10% in the alpha particle population. Okay. And I don't know about that last effect, how strong that is.
Yeah, and these deviations from what you might get from the back of the envelope matter in practical terms, because if you know them, then...
Yeah, well, if you know them, then you can perhaps calculate if the plasma goes unstable. Yeah. And there's then a very large transport suddenly. Yes. So you really have to know the detailed distribution function to do all these calculations. Yeah.
Sure. Yeah. Still on the back of the envelope theme, and perhaps for people who are not fusion plasma specialists, if you were going to do a back of envelope calculation, what sort of equations would you use? How would you set about it?
To get the alpha particle...
To get a guess, yeah.
For the alpha particle distribution function.
Precisely.
Ah, right. So that is a Fokker-Planck type of equation. There you can assume that it's isotropic, then it doesn't depend on the pitch.
Yes.
And then it depends also on the critical velocity, which is the velocity where the heating of electrons is equal to the heating of ions. So this distribution is actually quite complicated, because at large velocity you will heat firstly the electrons, and then at lower energies the ions.
Why is that?
Why is that? That's a good question. So the electrons are fast because they have a small mass.
Yes.
So they will tend to interact with alpha particles that are fast.
Because
then they have more time to fly parallel and do the interaction. And then when you go to the slower velocity, then interactions with ions become more important.
Yes. You've spoken about your measurements on contemporary measurements, both in relation to three classes of energetic ions, those generated by neutral beams, by ion cyclotron heating, and by fusion reactions. For eta, are the deviations that you measure likely to be more or less important than they are in contemporary experiments?
That's hard to say, because we don't have experimental data. So which deviations should be more or less the deviations from the classical...
So in eta, is the alpha particle population going to be more or less Maxwellian than it is in jet, for example?
I would say the alpha particle distribution is absolutely not Maxwellian, because it...
Well, when I say Maxwellian, I mean thermalized or...
Yeah. Okay. I think it's about the same.
Okay.
I would not make any difference. The parameters in jet and eta are, I mean, of course, jet is smaller, but the parameters are rather comparable.
Though eta plasmas will last for many fast ion slowing down times, which isn't really the case in jet.
The plasmas in jet last seconds, and the slowing down time is something like hundreds of milliseconds. So there are several slowing down times, at least in the jet.
Do you feel that's enough to establish equivalence?
Yes.
You mentioned just now orbits, and that's something I'm very keen to explore. That is the question of how the individual particles moving in the toroidal magnetic field, that's a deterministic Hamiltonian type question, how that single particle level of physics interacts with the collective velocity space distribution treatment that you're measuring and relating to the theory of. So if we turn to figure 111 on page 17, which is also the slide 7 of your talk just now, I find it so interesting that could you give us a sort of 5-minute mini lecture on the physics that underlies these extraordinarily shaped distributions, both in terms of wave-particle interaction and in terms of particle orbits in the toroidal field?
Particle orbits in the... Okay. So what happens here is that we have frequency, we shoot in electromagnetic waves, and the frequency of those waves is tuned to the ion cyclotron frequency of the ions. And then you have to have an interaction of the wave electric field with the orbit of the ion, which is a gyro orbit that I'm now referring to. And if that has the right polarization, so it goes in the right direction, this electric field, then it can accelerate the ion on its circular path. And when that happens, then not the parallel velocity will increase, but the perpendicular velocity will increase. So, and what that then really means is that you will go closer to a trap particle orbit. If that's what you mean with...
Indeed, yes. So how would the trapped passing boundary show up in this sort of figure? Where is it?
Oh, the trap passing boundary, that would be some graph like that.
Okay.
Yes. And those particles here with the small perpendicular velocities are going to be trapped, and the large parallel velocities can pass.
Sure.
Yeah.
But as the heating continues, passing particles will be transformed into trapped particles whose orbital turning points are on the vertical chord of the magnetic resonance.
Yes, that can happen.
Indeed, must happen.
Yeah, okay, it must happen. Let's say that, yeah.
So I'm just surprised that the trap passing boundary is so far away from this here. Are these particles all trapped, deeply trapped, or?
Yeah, these are all trapped particles. I mean, I think the passing particles are rather in that region here. Yes.
Okay.
Yeah.
Thanks. Again, some fascinating basic physics. The energetic ion populations, the three categories you've mentioned, they are distinct from the far more numerous thermal particles of the plasma whose fusion reactions generate the alphas, or into which the neutral beam ions are injected, or within which a minority ion population is heated by radio frequency waves. And they're different in particular in terms of their characteristic length scales and time scales of motion. Could you say a little more about that? Why they're different, how much they differ?
Yeah, so I guess one of the most important parameters is the Larmor radius, and that should be normalized by the size of the device, so by the minor radius.
Yeah.
So if the particle becomes more and more energetic, then the Larmor radius, which is mv perpendicular, so it's proportional to v perpendicular, it becomes larger and larger.
Yeah.
And when that happens, then it becomes larger and larger also compared to the size of the device. So your particle has a tendency to leave flux surfaces very substantially, whereas thermal particles are rather attached to flux surfaces. So they just go, if you see a poloidal direction, they're going to go in these egg shapes that we typically have in tokamaks.
Yes, indeed.
But the fast particles do not do that at all.
Sure.
They drift a lot off those surfaces. And that can also be seen from the drift velocities, because both the curvature drift and the grad B drift are proportional to the energies of the particles.
Yes.
Yes.
And indeed, mentioning those two drifts, among their consequences is that there are entirely new frequencies for energetic particles that would not really matter or arise for thermal ones. I'm thinking in particular of the toroidal processional drift.
Yes.
Could you say a few words about how that arises?
Yes. So particles, they bounce.
Yeah.
That's a trapped particle in the magnetic field. So you have a banana shape.
Yeah.
And if you view that from the top, then you also get a banana shape. And the tip of that banana is going to drift around in each precession. And then that drift that can be characterized by drift frequency then, that can also resonate with a variety of modes in the plasma.
Sure. So these orbital effects that we've been exploring, in general terms, do you feel they matter more for, say, ICRH heated ions than they do for alphas?
No, I wouldn't say so, because both are energetic particles.
Yeah.
And both are in a similar position in velocity space, so
Yes.
they will have the same effect. Of course, the mass is different, so there may be some difference, but it's not the heating method that really determines that.
Okay. So as a proxy for alpha particles, when you do not have deuterium and tritium, how perfect are ICRH particles?
Yeah, so they are missing usually the parallel component of this alpha distribution.
Yeah.
But you can, of course, study a variety of effects. Mm-hmm. In fact, you can also generate tails that more look like this and go into the also into the parallel direction. Mm-hmm. Which we are doing now at JET with this 3-ion scheme that will also increase parallel velocity.
Sure.
Yes.
Okay. And my final question on orbital effects feeds back into your work on Bayesian inference, which underpins much of your very successful applied work. To what extent, in the Bayesian sense, is knowledge of orbits a prior?
In this approach here, I'm not using the orbits at all.
Right.
But there can be an inference in a three-dimensional space, which could be the three constants of motion, which is the energy and the magnetic moment and the toroidal momentum, that then characterizes the entire velocity, the entire distribution function of all ions in this rather complicated phase space, but it really hits all ions. And in that phase space that is three-dimensional, each point would correspond to an own orbit. Yes. So if you do an inference in that, then you can make, then you can use the orbital information. And my new PhD student is now working on that in collaboration with our colleagues in D3D.
Okay, I hadn't realized that at all. So you're kind of concurring that there is additional information in the information theoretic sense, in the essentially deterministic Hamiltonian information that we have, and that is going to be incorporated in your Bayesian approach.
Yes, you could say that, but I would take a rather practical approach. Sure. So if it depends on what measurements we have available. So if we have only two chords, like a jet at the moment, then I think it is going to be very tough to make an inference of a three-dimensional function. So also the data that you have available has to match what you want to infer. So for the, like say we have, for this jet example that we showed, we have about 500 data points in the spectra. So then I should, because it's a matrix problem, I should have about 500 unknowns that I can infer roughly. It can go a little higher and a little lower if I want to make a slightly underdetermined and overdetermined system of equations, but it should be in that ballpark. So if I then go to a three-dimensional inference, then you don't get a lot of points that we do. But we'll try our best. Okay,
but there's a kind of zeroth order single bit piece of information there, for example, that high V perp over V particles are more likely to be outboard than inboard.
Yes, that kind of information is contained in the orbit. That's right. So if we use that, but I think it has to be in a three-dimensional space because orbits are characterized by three constants of motion. Then the orbit is clear. Unless there is a very strong, so that basically requires the tokamak to be axisymmetric, which it in reality isn't because you have magnetic field coils, but that assumption we are going to make.
Sure.
So in the Hamiltonian picture, that is a nice theoretical picture, but I'm not sure how well it actually holds in real measurement data. Time will show.
Okay, fine. Well, I have enjoyed our little intellectual workout over the last half hour or so. A final question would be, if the audience was composed of 16-year-old high school students who had just been bussed in, and you were asked to tell them the single coolest thing about your research that will convince them that physics is fun and that they ought to be doing it, and your field is a good one. What's the single thing that you do that you would tell them about?
I think I would tell them that I'm much looking forward to the party at ITER when we in 2035 have a Q = 10 where we actually generate more fusion than we put in.
Okay.
Yes.
But for the MTV generation, they might like more rapid gratification.
I don't think we have that.
Oh, come on! There must be some bit of physics that you'd like to share with a 16-year-old.
Okay. The physics. I did get most email correspondence on the figure of Pac-Man that I showed.
Yeah.
That triggered a lot of responses.
Mm-hmm.
But when it comes to physics, I think then I would speak about the alpha particle population that we're going to make very soon at JET. Mm-hmm. So this is the next best thing that we have to ITER, and I hope in the end of this year, I should say now, we'll have fusion experiments at JET.
Okay.
And that I would think that should hopefully capture the interest of a 16-year-old.
Fine, yes. Well, I'm delighted to hear you give that example, because that is indeed what captured my interest at an impressionable age. So at this point, I think I'll quit while we're all ahead and hand over to Professor Fasoli.
So thank you, Professor Dendy, and then I'd like to invite Professor Fasoli to the podium for further discussions on this thesis. Please go ahead.
Thank you very much. I take the same chair as my predecessor. So I know we will do the discussion with closed doors later on, but I can already say it was a great pleasure to read your thesis and also to listen to your presentation. Both show a very good capacity of also explaining very complicated concepts to people that are not necessarily experts in the fields, which is a difficult thing, actually. So congratulations for that. Congratulations for your work. And I would also take the opportunity to congratulate everybody else involved in your work. Of course, the students that work with you, but also the infrastructure and all the management of the group and of the university, because this is a very good demonstration. You can do top-level research in fusion, which is always done, people claim, in very big labs, very big centers, very big groups. You can do that at the cutting edge, also in small groups, as long as the quality is there. So it's really a congratulations to you, but also to everybody involved with this work in this place. It's also good that you show that fusion R&D can be at the cutting edge of physics in general, not just in engineering aspects, but also of physics, and that you get input from fields that are not necessarily within fusion, within plasma, within physics, for example, applied math, tomography, and so on. So all of this is really going to your credit, but also the credit of your group. So I structured my questions into two parts. The first part, a little bit more technical and diagnostic part, not on the details of tomography, because I know Professor Bolson will ask a few questions on that, but perhaps on the measurements as such, and also on how you can expand those. So first of all, my question to you in general is, what is the weakest link in your chain of measurements? You put together several pieces of information from different diagnostics, and at the moment, how do you perceive the weakest link in that, and what would you propose to do to actually improve that?
Yeah, I guess the weakest link that I'm always worried about most is systematic errors in any of those measurements, because they are, of course, very hard to track. Otherwise, we would fix them. But it could be that we, for example, have a calibration of a measurement wrong, and then we would have that would, of course, show when you propagate this into the distribution function. So I guess that the answer is that it is really important that you do not make too many systematic errors in this process, and you have to try and identify those kind of errors. But that's, of course, difficult.
So what would you do if you're given unlimited amount of resources? And I know this is not a completely realistic question, but suppose you had unlimited amount of resources, where would you attack?
I would install way more diagnostics on all machines than we currently have. Usually when I do these analysis, then all the time I'm in a photon starved or yeah, what should I say? I don't have as much diagnostic information as I would like to make a good measurement of the velocity distribution function.
Do you mean more lines of views?
Yes,
or more
lines of views and higher spatial resolution. You can do a lot with just moving the instruments to some other viewing angle. Then you cover a completely different part of velocity space, and then you can, with the same diagnostic installed in a different way, really make good complementary measurements. And then, yeah, you also have to worry about which kind of energies you want to measure. If you have low energies, then you could use fast IND alpha spectroscopy that I've used a lot in collective Thomson scattering. And if you go to very high energies, then it's probably better with gamma ray and neutron emission spectroscopy measurements. So, but so it depends on what is the distribution function that you have in the plasma, what kind of diagnostics I would install. Yeah.
So this is a perspective of someone who measures things. Now, of course, you have to put together the measurement with the modeling side and then form a physics understanding and predicting capability, perhaps even control capabilities. Are we not pushing too hard from the diagnostic point of view, in view of the fact that there are uncertainties in the models as well, both in input and in the mathematical tools and the mathematical hypothesis? Or do you think we have to catch up with what the models can do? Where is the...
Well, I think the only way that we can make any progress at all is to compare whatever we measure with what we simulate, and in that way we hope to find some new effects. And so really we have to develop both capabilities. We have to model and simulate and measure in a better way. So that's the only way to really progress.
My point is that we can progress only if the comparison theory experiment becomes somewhat quantitative, because we've been going through decades in which we were happy because we were seeing the same kind of blobs, the same kind of color things on both sides. I think now is the time where we have to go quantitative. So how do you see this quantitative approach in the comparison? I would call it maybe validation rather than comparison of the models from the experiments, and where are we with that? Do we have the tools that we don't have the data, or do we have the data, we don't have the tools?
Yeah. So I think it is in principle very possible to now make quantitative measurements of velocity distribution function that we can directly compare with the numerical simulations. But for that we need correctly scaled and calibrated measurements, and that can be done by, for example, fast IND alpha spectroscopy and collective Thomson scattering. There we have an absolute scaling of the spectra, and that's okay. So if we use those diagnostics, then we are already capable of getting the right quantitatively good agreement. We are a little behind on neutron emission spectroscopy and gamma ray spectroscopy, where it's quite hard to get the absolute scaling right. So if that could be developed to have really an absolute scaling, if I have one ion in the plasma that's going to generate me that many gamma rays on the detector, that would be great.
What do we miss for being able to do that?
I'm not sure how to actually do that, but what I do know is that the diagnosticians for gamma rays and neutrons are really working on to get absolutely scaled spectra. But I think it is difficult because there's really not that many gammas and neutrons generated.
You mean in the present experiment?
Yeah.
Something that's very fashionable, and I don't know if the jury is out, at least as far as I'm concerned, it is, on the usefulness in this kind of work. What if we were applying massively this modern analysis technique based on machine learning, artificial intelligence? Would we really gain significantly compared to what we're doing now?
Yeah, I think so. We could. Those kind of techniques have been applied in tomography, and I think they will be applied also. And I would like to try and apply artificial intelligence on those graphs. There's basically three ways that you can use artificial intelligence for. I think the most promising is, I guess, to measure, to get an estimate of the regularization parameter lambda that determines the matching between the data fitting and the smoothness. That could be determined by artificial intelligence, just by telling the computer again and again to training what value would I pick. And that is actually, it's always a little uncertain what that parameter is exactly, because there are several ways to determine that parameter automatically, but they differ by some factor of 3 to up to 10 or so. So, and there I think I'm actually, as a human, better than the methods to pick the right parameter. I usually pick many parameters and then compare the different solutions, so I have an estimate of which one is the best. And I think that kind of job could be done by artificial intelligence too. In the brute force way of using artificial intelligence, there you would just feed the measurement on the detector and then tell the algorithm what is a distribution function, but you do not actually tell the physics link between those. And I'm a little doubtful about that, because why would I not tell the computer what is the physics that determines the link between the measurements and the distribution? But you don't have to, and there are tomography applications that do just that. So that is the second big field, and that is applied in other areas in tomography like that, where you don't actually tell where are your sightlines. And the third way is sometimes there appear artifacts in the tomographies, and that is some spurious feature of the solution that we know is not there. And we can actually test that by making a test distribution and make some synthetic measurements and try to invert it back. And then we can see that sometimes there appear in certain places in velocity space some feature that should not be there. So artificial intelligence could then also be used to track that and suppress those artifacts. But that's of course a little risky, because maybe it's physics. So we should be a little wary when we do this. But those are the three ways that I would like to try in the future, for sure.
So still on the diagnostic part, ultimately we want to make fusion, and we want to control a system that's optimized to make fusion without damage and so on and so forth. So in other words, we want to in real time act on our system. What is the potential for a real time application of this kind of approach?
Yeah, the problem that I'm solving here is actually quite small. So we only have, it is determined by the amount of measurement data that we have. So we have about 500 measurements. So this inversion here can be something like 20 by 20 or 30 by 30. So it's a 900 parameter problem. When you go to the doctor, then that's millions of points that you need to do an inversion on your inside. So really the problem is quite small. So if we have computer power, we can actually do this quite quick. But I would at this point not go so far that we can use it for control. My goal is at the moment to have some immediate diagnostic after the discharge, where you can determine something on the time scale of maybe a few minutes. That is typical also for a doctor-patient interaction. But if you go to control and you really want to go down to milliseconds, I think we might be a little further in the future, but I think it's possible because the problem is so small.
I think maybe milliseconds is not even needed for big plasmas. Maybe tens of milliseconds will be enough, right?
Yeah. So that'll be my declared goal when I have the movies automatically generated. Yes.
Now, one of the reasons why we want to know this distribution function is that there are interactions with instabilities, and they are dictated by resonances that are complicated and populating the phase space themselves. So my question is, can we not use also those resonance and events they are causing in the plasma to actually inform you or give you boundary conditions, give you constraints on your reconstruction? Because sometimes these resonances are occurring anyway,
Yeah.
we like it or not.
Yes.
Sometimes they're benign, so there are small fluctuations that are observed,
Yes.
waves.
Yes.
And they have themselves a lot of information, so I wonder why you should not use them.
Yes, I have thought about that. What we will need to do that is, I mean, if you want to have the best use possible, you would need a forward model that tells you this is my instabilities, then that's the effect on the distribution function. I think that would be able to, we would be able to implement that if there's a real forward model. But there can also be a little more soft information, something like if an instability occurs, then we are already sure that there must be a monotonically increasing function at some point. Yeah. For example, that could be added as a constraint on the inversion. So then I could say in that region of velocity space, I'm sure that the gradient of that distribution must be positive. So that information could be very valuable to feed the inversion. I haven't done it yet.
Okay, but it's in your...
It's always running in the back of my head, yes.
Okay, so perhaps I move to the more general strategy questions. So where do you think we are at, with respect to our capability of really anticipating what's going to happen in a burning plasma? A burning plasma is a plasma that's dominated by internal heating from the fast particles, in particular the fusion-generated alphas. What are we really missing? What are both the building blocks that we are maybe missing in terms of physics understanding, if any, or are we missing the fact that we had to put them all together in a way that we don't know yet how? What is your perception?
Yeah, so what is really new in ITER is this new regime that the profiles of the deuterium and the temperature are really self-organized in a plasma like that, because you generate the fusion reactions, and that generates heat, and that heats the plasma, and then that changes the profile, which in turn changes the reaction rate. So all that is now self-organized, and I'm not aware of any simulation tools that can really do that very well. I'm not aware of any. Maybe there are some, but I don't think we know a lot about that. So there I would make the approach that we should have a lot of measurements that can guide in developing those kind of models. But that you can only do when you really have the distributions at ITER when these burning plasmas are running. Before that, I guess it'll be more guesswork if that's going to be like that or not. So to have hard evidence, we're going to need the plasma in ITER.
So you don't think there is something we can still learn from the non-burning plasmas that we have today, or today until 2035 November-ish?
Yeah, sure, we can learn something, but not that aspect of the self-organization. That is, I think, very difficult to do on present machines when we control how much heating is added to the plasma.
But don't you think there are some aspects of the nonlinear interactions that we can still study that we don't really know the mechanism of, in particular using these velocity space reconstruction techniques and the resonances that we know in the plasma?
Yeah, we study if the distribution function can hit resonances, and then we have a redistribution because of that. I did several studies of that, but so far I haven't found a case where that is really very strong. But we are investigating if we can make studies like that, where we see an effect of the resonances on the distribution function.
Because I think this is a very important missing block that we still need to investigate before the ITER burning regime. Because if you, and you're the only one that can do it in the world, I think, see a situation in which there are no linear or chaotic regime in the wave-particle interaction, and that is visible on the velocity distribution in 2D, that's a fantastic piece of measurement, I think. That's a fantastic result. So I think we have to look for that before we really have the completely burning regime in ITER.
Yeah, we will need experimental time in that case.
I would argue for that experimental time to be given to you, because that's a very crucial point. So I'm moving towards maybe the end, but I still have a few questions if you don't mind. Not only do we need to make sure that ITER will work and will produce its power as anticipated, but we also need to make sure that ITER will provide the information that we need for it, because ITER will not be the reactor. What do you think we should do in your area of fast ion physics to maximize the output of ITER in terms of information for actually building the real reactor?
We need absolutely way more diagnostics. I think ITER is very heavily underdiagnosed. We only have those gamma ray and collective Thomson scattering measurements for alpha particles. But we should also try and get several more diagnostics up and running, which gets more and more difficult as we complete the construction. But we have several activities, for example, the ion cyclotron emission that could give us very valuable information of what's going on in ITER. And that kind of information that could really be tapped by the existing ICRF antennas. So there we have really a possibility to get more diagnostic information. And also the lost particles, they should be diagnosed better in ITER, where we should have several more loss detectors that can really tell us what is actually lost. Because if we don't have that, we'll be blind. So there may be some effect that decreases the performance, and we are not going to be able to assess it as well as we could, I think. So we are still fighting to get a lot more diagnostic installed on ITER. Also this oblique gamma ray that I showed an example of. It's actually quite a small detector that needs to be somewhere. So it's only that size. And we hope that we can fit that somewhere. Then we would be able to tell if alpha particles are going that way or that way.
I think it would be absolutely crazy not to do that. I will help you fighting for that. So let me conclude with a question similar to the last question from my predecessor, Richard. Suppose that 16 years old girl has a 19 years old or 22 years old sister, and she tells her, look, Mirko told me that it would be very exciting in a few months. There would be a new DT campaign on JET. The last one was at the end of '97. I had the privilege of participating in that. And so it's very exciting. But the older sister says, okay, why is it exciting? Why is it going to be different from '97? Because there's going to be less fusion power, less fusion gain. What are we going to learn more? How would you answer to this slightly more knowledgeable person?
Yeah. So back then in the '97 campaign, the wall material was
97. I'm not that old.
Yeah. So back then the wall material are such that they would not really be up for a reactor operation. And then since then ITER has been refurbished with beryllium walls, which can actually sustain a reactor environment. And yeah, you
but
could say that
in terms of fast ion physics.
In terms of fast ion physics,
your area.
Yeah, we have a lot less.
That doesn't care about wall. Yeah?
Oh, okay.
Not so much.
We have a lot less neutrons now than we had back then in 1997 by some factor. But I still think that we can do the same experiments, and also I'm not sure how much. I think there could be a chance to get a good fusion power here too in JET, with more relevant conditions for actual fusion power plants.
My answer would be much less modest. My answer would be, myself, Mirko Salewski, have a new way of diagnosing the fast time distribution, which we did not have in '97.
That's true.
So thank you very much, Mirko. I'm done.
And as already announced, the chairman of the committee, Professor Henning Friis Poulsen, also has a series of questions to you on the topic of, as was already also said, tomography. So please, Henning.
I will not be pretentious, I'll take this over here. So Mirko, The reason I take the word is because I have a common interest with you in the topic of tomography and in applying it. Like the other opponents, I would like first to congratulate on you on what is a thesis here, where it's clear that you've really spent some time on trying to make this, accessible for other people. And in this respect, I count as a layman, and it was very easy read actually, and I think I understood at least part of it. So for the, with respect to tomography, you present it as this is like medical imaging, but if you talk to the mathematicians, tomography is actually a very broad field, and there clearly are some differences. You have scalar tomography, vector tomography, and so on. And my first comment is I think that for this particular problem, I think you've been very clever in choosing the right approach. The Tikhonov approach seemed, and you've shown that this actually gives results. Even though that on paper looks simple, the equations, nevertheless, there are some details involved in this. There is, in particular, the stopping criteria, and there's relaxation parameter. And you can discuss, these. And since you are now, and I'm sure there's going to be some optimal solutions for this, but you're now comparing a number of different experiments. And I assume that the optimal setup could be different from these. So in trying to make a model that combines all the experiments, how robust is that, and how much time have you spent on these varying these parameters?
I would even say it's much worse than that. If you have one machine and you change the plasma conditions in that machine, and that can vary by a lot, like you can change the density and the temperature and so on, that has a very large impact on what regularization parameter or stopping criterion you use. So it's not even that on the different machines there can be large differences, but also even within one machine it can change. So yeah, that's the problem that is common, I think, to many tomography applications, that you always have to do something to choose the right stopping parameter. Or in my case, in this formulation, I'm not using an iterative approach. It's basically the lambda that you have to choose right. Yes.
So another thing that's already discussed is that for tomography to work, this kind of tomography, you are relying on your system parameter. And the question is, and you have some estimates of uncertainties, but they could be subject to various kinds of systematic errors and so on. I think we heard some of them. So that leads to a topic which is coming up, which is quantification of the uncertainties in tomography.
Yeah.
Have you made some thoughts of that and what to do?
Yeah. That is a very important subject. So there are basically, I think you could say, 4 different types of uncertainties in this kind of tomography problem, and that's maybe shared with most other tomography applications. You can have the uncertainties in the measurement data, which is just the noise that you can just propagate into your inversion and assess it. I don't usually do that anymore because the result is always the same, because the regularization takes care of that. So I suppress these kind of noise uncertainties in the first place. That's the idea of the regularization. Then the second part is that the system matrix that can have some nuisance parameters that will influence that. That is usually not a big problem in normal tomography, where you just have sidelines and then you know your system matrix very well. But in this case, it's really determined by temperatures and densities of the plasma and so on. And all these are not really that well known. They come with an uncertainty. So there's an uncertainty in this matrix that you somehow have to characterize. And that can also be done by Monte Carlo sampling. Usually I've found that for all problems that I've found, that is usually very small. And then the third part is the very systematic error that we make because of the regularization itself. So when we have some function and it's got small structures, and then we make some measurements, add noise, and try to invert it back, then we have a tendency not to be able to regenerate those very fine structures when we use a Tikhonov regularization. So that is a type of systematic uncertainty, and the larger this regularization parameter gets, the more this becomes. So it's really, if you choose it very small, then you get a measurement that fits the data very well, but it's just jitter. And if you choose it very large, then you get a very smooth function, but it doesn't match the data very well. So this is this kind of balance that you have to make between those two uncertainties. And then lastly, you have always systematic uncertainties in the measurements themselves. There could be a systematic error that you're making, like you have a wrong calibration of the measurement. And that's, of course, not good if you have that. And, yeah, we're trying to track that down.
Yeah.
Yeah.
And on that note, I mean, I think one difference between, say, classical tomographies, in the classical tomography, essentially all the measurements are more or less the same because it's the same detector used and so on. But here, and I find this quite intriguing, here you're using a number of very different measurements, and you're trying to combine them. And I would guess that there's a likelihood that one of them probably is more wrong than the other. I mean, somehow there's a systematic error in one of them, not the others. And my question is, couldn't we actually figure out which one? Because I understand that right now, I mean, you want more projections and so, but assume you had it. Couldn't you essentially use that to backtrack which of the instruments is working the worst? I mean,
yeah, I think that would be possible. I would, you could do that if you have enough. Then you could switch off the different diagnostics one by one and see which kind of inversion you get, and then you can try to make the inference which one is the bad one. Yeah, you can also try it by a kind of forward modeling, where you compute measurements from your inversion and then see how well that matches the different signals that you use. So yeah, there are ways to try and track such systematic uncertainties down. Yeah, I would hope so.
Well, I think that concludes my questions. Thank you very much.
So that means that we are coming close to the end of the formal proceedings of this doctoral thesis defense. I'd like to thank the assessment committee, the two official opponents, and the chairman of the committee for the large work that they have done. The big work in reading and assessing the thesis before coming here, and also the work in preparation for this the defense in itself, and participation in the proceedings here, with questions and discussions that has probed the depth of the candidates' knowledge. And as I already said, immediately after the defense here, the assessment committee will convene separately to make a conclusion and decide their recommendation to our academic council. And the academic council will then take the final decision on awarding the degree at their meeting on February 17th. Now, in my introduction, I mentioned Ørsted and the discovery of electromagnetism. Ørsted's description of the phenomenon was purely qualitatively. It consisted of a text and some drawings about the phenomenon. Ørsted was not skilled in mathematics. In a sense, this perhaps because of his big influence, not just in the formation of this university, but also later on in the formation of the Faculty of Science at the University of Copenhagen. The formulae describing electromagnetism were not formulated here, but formulated by Maxwell. That was also mentioned by you at the beginning of your presentation, half a century later, after the first discovery. And also, mathematical physics was not a big thing in Denmark after the formation of this university. It only came later. Now, we have remedied that small flaw, and I think we have seen a good example of that today, how mathematics and physics can be used in conjunction to make new inference about nature, with potentials in engineering and providing a big impact on society. I'd like to thank Mirko for the thesis, the enlightening presentation, and the defense that you gave here of the thesis. Now, we cannot congratulate you on the degree yet, but we can congratulate you on completing your part of this process. Doing the research, writing up the thesis, preparing the lecture, and participating in the defense. And therefore, I would like to congratulate on that and present you with this small bouquet of flowers.
Thank you.
And now I'd like everybody to step outside in the lobby outside, and please help yourselves at the to a drink and a little bit to eat at the small reception that will be ready out there in a little while. And then we'll look forward to the assessment committee returning from their private meeting to hear their conclusions. So thank you everybody for attending this doctoral defense that I now officially declare closed.